Hello guys, welcome to the channel. In this particular video, I will explain the problem predecessor and successor. So let's see the problem statement. Here is the problem. It says that you are given a BST with a root node with a key part as an integer, and you need to find the in order successor and predecessor of that given key. Now, if either the predecessor or successor is not found, then set it to null. Now, one note is given about the predecessor and the successor. It says that in an in-order traversal, the number just smaller than the target is the predecessor and the number just greater than the target is known as the successor. So let me explain with this example. So one tree is given here with the key value as 8. So for this tree, if I try to write the in-order traversal, then it will be 1, 2, 3, 4, 5, 6, 10, 11. So this is the in-order traversal. Let me write in order here. So in order, right? And now the key given to us is 8, right? So the value just smaller than 8 is 6 and the value just greater than 8 is 10. So 6 and 10 is going to be the predecessor and the successor for this particular example. So you can see the output here. Even let me take one more example. So for this example, let's say the key value which is given to us is 1 instead of this 8, right? So you can see that we have the successor, right? The successor value is 2, but we don't have any predecessor. There is no any value which is just smaller than 1 in the in order traversal. So in that case, the predecessor will be null. I hope you have understood the example. And if you take the key as 11, so in that case, successor will be null. So this is what the problem says. It says that if either the predecessor or successor is not found, then set it to null. So I hope you have understood the problem statement. Let's talk about the solution. So here I have written the same example which is given here, and now this problem is quite similar to the one I have explained you yesterday. So in that case, in that problem, you can see that first of all we started with considering our tree as the binary tree. So all we need to do is in the first approach, we can store the in order traversal, right? So if you guys are aware of how we do in order traversal, then it is good. And for those who don't know, I'm going to explain. So what we do in order traversal is, first of all, let me write a function. So this is the function which is going to take only one parameter, which is root, right? And now, first of all, if my root is equal to null, if my root is null, let's say I have a tree where root is equal to null. So what is the in order traversal in that case? An empty list, right? So I'll simply return. And if my like root is not equal to null, then we have tree like this. So what we generally do is we start from this position, then we move to left, then we move to left, we keep moving to the left until we have a null node. So you can see that if I try to move left from this node, then I will have a null node, right? So I will come back and I will print this. How to write this? I'll simply write calling the same function for the root dot left. So I'll write in order root dot left. And if I write this, then whenever I come inside the function with the root which is not null, so I will move to left. So this is how from this point I'll move to left, then left again, then left again. And if my root is equal to null, let's say my root is null, so I'll simply return, right? And when I return, then I will come to this position, and at this position, first thing I need to do is print the root, print root data. And after this you can see that I'm done with left part, right? So after this I need to go to right. So I'll write in order root dot right. This is brief about the in order traversal, and this is the function which is going to perform the in order traversal. And if you guys see here, then you will find that we have to store the in order, right? So we are going to make a list. I'll write a list here which is an empty list initially, and this list is going to store the in order. So instead of printing the values, I need to store the values. So I'll write list dot add root data. So if I like run this function, if I call this function, then I will have all my node values stored as an in order traversal. So we just need to call the function, and once I have stored the in order traversal, Once I have stored the in order traversal, so I can simply perform a search, right? I can simply search over the array to find the element which is just smaller than the key value and just greater than the key value, and this way I will have my answer. And talking about the search, so you can see that uh, I want you to think of one thing, and even this is an observation. Whenever we have a BST, then the in order traversal of that BST always gives us an like sorted order. So these element will always be in sorted order because we are given a BST here. So we can perform the binary search as well. Binary search. So this is a simple problem. First of all, we need to perform the in order traversal, then we can perform the binary search. I'm not going to implement the binary search here because this is quite simple to implement and this is not even the optimal approach. So once we perform the binary search, then we will have the answer, right? So what is the time complexity of this approach? The time complexity is going to be of n for like for the in order traversal, which is going to iterate over every node in the tree, and after this I'm performing a binary search, so this is going to give us the O of n, right? So this is how we can solve the problem using the first approach, and this is the time complexity, right? So can we optimize this? Of course we can optimize this. You can see that we are given a binary search tree, not a binary tree. Can we use this feature? Yes, of course we can use this property. So how we can use this? First of all, let me draw the same tree. So I have 10, then I have 2, then 11, then I have 1, then 5, then 3, then 6, then 4, right? This is the tree which is given to us. And for this tree, you can see that as a usual binary search tree, we have all the values on the left side as the smaller than root value, and all the value greater than like all the value which are on the right side are greater than the root, right? So this is how a binary search tree works. Now let me write the sorted order. So the sorted order, I'm going to take any random sorted order. Even let's write this particular sorted order. So I'll write 1, 2, 3, 4, 5, 6, then 10, 11, and let's say the key value is 5. So key is going to be the 5 for this particular explanation, right? And now what I'll do is, let me draw a box here. Inside this, I'm going to write three possibilities which are there. So let's say this is our key, right? So there are three possibilities. If my, let's say I'm passing through every node, so I'm currently at any random node. So let's say this is the node, and node value, there are three possibilities. Either the node value is equal to node data is equal to k key, or the second possibility is node data is greater than key, right? So node data is greater than key, and the third possibility is node data is smaller than key. So let me write else here. So these are the three possibilities, and I'm going to explain each possibilities to you. So let's say my node data is equal to key. This means that I'm at this node, right? Because the key which is given to us is 5. So from this position, the value which is just smaller than like the key value will be always on the left side of the tree, right? And the value which is just greater than the given key value will be always on the right side of the tree. So successor will be on the right side and predecessor on the left side. So I need to call both. So what I'll do is, let me change the color here. So I'll write in order root dot left, or I'll write node dot left, right? So I'll write node dot left. This is the first thing. And the second thing is, I'll go to right side. So in order node dot right. This is what I can do. And after this, let's say my node data is greater than key. So consider I'm at currently at any random node on the right side. So let's say I'm at this node 11, and you can see that my node data is greater than the key value, right? Key is 5 and the node data is 11. So as this value is greater, so there is a possibility then that this value can be successor, right? Because I don't know about this value. So I can write my successor is equal to root. This is the first possibility that we have, and after this it is also possible that there are values on the right like on the value which are smaller than the current node value, right? So you can see that even the successor is smaller than this 11. Successor is 6, the actual successor. So there is a possibility then that if I am at 11, I am at this current node, then real successor is smaller than this node. So in that case I need to move to left side. So I'll write in order because I'm checking for the smaller values. So smaller values are always on the right, left side. So I'll go to node dot left. Similarly, if the node value is like smaller than key, so key is greater. So let's say I'm at any current random node which is 1. So let's say I'm at 1. So first of all, I'll write predecessor equal to 1. Why? Because there is a possibility that if this node is smaller, then this is the predecessor. So I'll pre equal to root. This is the first thing that I will do. And there is one more possibility that any value which is greater than like this one is actual predecessor. So you can see that 4 is the predecessor. So I'll try to move to right. I'll try to increase this value and check whether this value is in the tree or not. So I'll write in order node dot right. So this is a function. When this function, oh, what is the function? Function is actually in order. So this function is going to take two parameter. Again, you can so one is node and the second is key. So you can ask me why I have not written key here. So you can write the key, it is the pseudocode, right? So I'm not like concerned about writing the actual right code. So I will of course surely definitely show you that implementation. So this is the code that we have. This is the pseudocode, and we need two more values. You can see that I have successor and predecessor. So let me take these as the global variable. So I'll write pre and successor, right? So these are the global variables. So this is all we need to do. I hope you guys have understood this thing. What is the complexity of this code? So talking about the complexity, you can see that I'm either going to left side or going to right side. So there are only two possibilities that I can have. So from this 10, I'll go to this 2, then I'll go to this 5, then I'll go to this 3. This is the worst case that I'm discussing. Of course, this is not the actual case, but in the worst case, I can go to this 2, then this 5, then this 3, then this 4. So this is the maximum distance between the root and the leaf value. So what is this distance? This distance is actually the height of the tree. So the complexity in worst case can be O of height of the tree, right? So this is the complexity. I hope you have understood this thing. Let me show you the code now. Okay, so here is the code. I have written the Java code on the left hand side and C++ and Python code on the right hand side. So let me explain the code. I have taken two global variables here. So let me uncomment this. So these are the global variables. I have commented this because in the in the code on GFG, this thing is present in the like driver code, right? So that's why I have commented this thing. And now this is the function. The function is very similar to the one I have explained you. You can see that there are three possibilities: smaller, greater, or equal. So now this is something which is I'm using the reference call by reference here. So I'm making an array and then I'm simply passing as the parameter and then I'm simply assigning the value. So this is what I'm doing. And one more thing is, okay, let me remove this thing. And now this is the C++ code, right? So you can see that the C++ code, I'm doing the same thing. I have made an array which is for call by reference, then I'm passing as the parameter, and this is the function. And now this is the Python code. Okay, so I think I have missed out one thing here, that okay, I have not discussed one thing. If my root if my node is null, if my node is null, then simply I need to return, right? And this is an obvious thing, I think. So this is all about this video. I hope you guys like the explanation. If you guys like the explanation, then you can hit the like button. Thank you.